Then, one of the last posts was about the Brascamp-Lieb problem. And I wanted to, it would have been nice to claim that I was like, look how prescient I was. But it's exactly the opposite, because I didn't see any relationship between them, all just nice examples of some phenomenon. So let me just tell you about some general setup. Now you can come to this from having no background or having ignored this introduction. Suppose you have a convex body in Rn, and so this is a set of constraints. You can think about yourself as sitting somewhere in this body, and then there is some control function. So I have some desires in the world represented by a control. So it's a vector field on the convex body. At every point, there's a vector pointing somewhere in space, and maybe this vector field is varying in time. And then you can think about the natural dynamics that arise there, which is just to flow along this vector field, right? If you're sitting at xt at time t, then you can think of the algorithm which just moves a little bit in the direction of the vector field. Let's assume that it's, say, continuous in time and in the Euclidean topology here. Okay, and so this, of course, is great until you reach the boundary of this polytope, and then you cannot just keep flowing along the vector field if you'd like to stay inside the convex body. So you can imagine the kind of things you might like to do, something which still kind of flows along the vector field but doesn't leave the body. So there's just a very natural way to change the algorithm, which is just to project back, right? So you're sitting in the body, you move along this vector field a little bit. Now if you're outside the body, just project back to the body, and this gives you some dynamics that stay inside the body for all time. I mean, assuming that everything is sufficiently smooth. But when you decide that you're going to project back, though, here there's some arbitrariness to this projection. We're doing projection in a general sort of in the Euclidean metric. But once you're going to decide to project back, you could say, what do I need to define locally around where I am some projection? You just need some Riemannian structure to define this projection back into the body. Just at every point in some local inner product that say very smoothly over the body. So you could define dynamics in this general setup. I give you a Riemannian metric on the convex body, and then you flow along some vector field and do projection with respect to this Riemannian metric. And the problem is, at that level of generality, you don't have a lot of control on the dynamics. There is, if the geometry can change from point to point, then say if you were doing gradient descent, you might not have any control on how fast you converge to some optimizer. But there are a set of structures that carry with them some global control, sort of stability on these dynamics. Those are the Hessian structures on Rn. So these are the Riemannian metrics which come from fixing some global convex function on the body and then taking the inner product to be like this. Okay, so this gives you at every point in space. So if this function is take a function which is convex, then its Hessian is positive definite. This gives you an inner product everywhere. And now you can consider this algorithm with respect to this inner product. Is the basic idea what I'm saying clear? I'm just sort of, it's somebody is giving you this at every point in time, this vector field. I want you to move in this direction. I want you to move in this direction. So you try to accommodate, but you can't leave the body, so you project back. And then I'm suggesting that to project back, you use a Riemannian metric coming from one of these Hessians. Okay. This is okay. You can give this every name. If you describe it at this level of generality, it's it's almost, you can think of it as all of interior point methods. It is often called mirrored descent. So the point is, I've described things in continuous time, in which case a lot of these are exactly the same. Of course, computationally, you need to discretize this process, and the way that you do it might depend on where you are and how things look, and then you get different algorithms. So,
conjugate gradient, the geometry is not changing. In conjugate gradient, it's the same thing, but the Hessian is fixed for the entire space.
Here I have a fixed Hessian. I'm not changing the Hessian.
No, the Hessian depends on the point. In conjugate gradient, the Hessian is just the matrix that you're trying to solve.
Okay, so I mean, but in this case, it is a special case of this. But you're just saying it. No. Okay, so you can actually describe explicitly here the dynamics. This system is it doesn't fall into the setting of classical ODE because well, you can see that it's non-smooth. I mean, if a point here hits the boundary, then suddenly the trajectory changes in some non-smooth way. But there is a whole field of projected dynamical systems and these differential inclusions. And using the basis of this, you can describe these dynamics very explicitly. So, okay, so they look like this. You start at some point in the convex body. Then, at every point in time, you can describe the direction in which you're moving. It's the Hessian times the Hessian times derivative is equal to this. And okay, so yeah, so this is very. Okay, so what is it? It's the vector field. Like this is the most natural thing. This is where you'd like to be moving. But then, of course, you cannot necessarily. I mean, we're constraining you to remain in the body. So there is some term coming from the normal forces, the constraints pushing back on you to keep you inside the body. That's this lambda t, and this lambda t lies in the normal cone at where you are. So, and just to remind people, the normal cone is at a point of a convex body. It's just the set of directions that leave the body, basically, that are so, you know, if I take something in the negative of the normal cone, it's always something which is moving back inside the body. Okay, so you can, yes?
Lambda of t is 0 outside the boundary.
Yeah, so if you're not on the boundary, then this, yeah, so then, well, it doesn't say so here, and in fact, it's, yeah. I mean, definitely lambda t is 0 outside the boundary. It just doesn't follow from what I'm saying here. Yeah, so if you're inside, then what you're just doing is unconstrained flowing along the vector field. Although if you take some, I mean, if you take some, well, you can take some affine slice in Rn so that they're always on the boundary. So this is sort of the general, you know, it's the picture is misleading. In almost everything we do, you'll be on the boundary the whole time. So. Okay, so let me just, yeah, so, you know, so. We needed these general dynamics in a recent paper with Sebastian Bubeck, Michael Cohen, Yin Tadley, and Oleg Madry. But, well, I put the reference here only for the sake of my co-authors in the sense that these dynamics are not particularly surprising. And this theorem has never been stated like this, I think exactly like this. So there's a reference for it, or we proved the theorem. What's interesting about this setup is that there is a Lyapunov functional that controls convergence in some sense that I'll tell you about now, which, again, if you're familiar with these things, is not surprising. This is the Bregman divergence associated to the functional phi. And this has the really nice property that, in a sense, this algorithm is always improving. Okay, so in what sense is it always improving? Well, for any point y inside the convex body, if the vector field, you know, points, you know, in the direction from xt to y, so if the projection of the, you know, direction from x to y has a positive inner product with the vector field, which means that in the unconstrained setting, you would be moving towards y, right? Like if there's no constraint here and you move, and the vector field is correlated with y minus x, of course, and if you don't have to project, you're moving towards y. This tells you that even if you project, you're moving towards y. By the way, what I said before, in just in the Euclidean distance. This tells you that if you use these dynamics, sort of this projected gradient flow, then under this Riemannian geometry coming from the Hessian, then you still make progress in the same sense. So this functionally improves. Proportional, like for every point inside the body, you get closer to that point in this sense by the, you know, the amount that y is doing better in the vector field than x is doing. Does this make sense? What I'm saying? It's okay. So so in general, you can think. I mean, if the vector, so if you can think about the vector field, for instance, as giving me a little bit of information about y, and this says that if I move in this direction that's a little bit about y, then I will get closer to y in some sense. So, okay, you'll see some examples. Okay, we'll see some examples now. So this is just, and by the way, like this computation just, I mean, if you just take this and you plug it in, you see exactly what happens. And then the fact that there's this lambda t term here, it goes away in this inequality precisely because y is inside the convex body, and we know that lambda is pointing inside the convex body. Okay, so this is some very nice general setup. Let's just first see matrix scaling in this setup. So, yeah.
But actually, matrix scaling, yeah, if continuous time is nice, probably it was done, I assume, before. But this is how original matrix scaling was done, using Bragg projections.
I would say that Sinkhorn and Knopp did not think about it this way, but certainly Franklin and Lorentz thought about it almost exactly in this language.
No, before, there is this paper which is cited actually by Bregman. And moreover, my paper with Yanilos specifically used Bregman projections to analyze and even progress. And it's happened to be very related to capacity.
Yeah, well, yeah, that's,
Yes.
this is,
But anyway, but Bregman, I mean, if you look, Bregman was optimization guy.
no. I mean, nobody's saying this. This is a general. Nothing I would say here is. There's certainly nothing revolutionary on this slide. This is 30 or 40 years old at least. But you're saying, but 67 they were already describing themselves as.
Yes, that was not. But Bregman was. So actually, the funny thing, it was happening at the same time. That Bregman bound upper bound on the permanent, and that thing, it was at the same time. So it's like early 70s.
Yeah. Okay. This. But I mean, okay. So Sinkhorn and Knopp. I mean, first of all, this alternating minimization algorithm, very basic. One can come up with it without knowing anything. Of course, it's just something very natural to do. The first instance I know where it was analyzed in this setting was by Franklin and Lorentz, but.
His motivation was how to get the intersection of convex sets.
Yeah. Well, the question is, what are we?
By projecting, by doing Bregman projection.
Great, the question is just whether he analyzed matrix scaling.
Yes.
He did.
Yes.
Oh, fantastic. Okay, so why? Okay, so well, you should.
Not in many details, not in bounds. That was his example.
Okay, it's a great example. There are some. Let's just say this list of references is incomplete here. So I just want to say how you can cast matrix scaling in this setup.
So what's the connection between the vector field and the phi actually?
Yeah, so the way you should probably think about this is there is the phi gives you some geometry. We'll see in a second sort of how this comes into play. It gives you some geometry and some, you can think about it as choosing the correct geometry to work in that will give you nice control on the convergence. One basic way to think about the choice of phi is just that, if you, for various reasons, you might want, even in continuous time, this algorithm to converge fast. And so it would make sense, for instance, to choose a phi where the diameter of the body is small. I mean, okay, of course, there are two scales there. But for instance, even for the simplex, if one chooses the entropy, in general, the diameter of the underlying body will be smaller than if one chooses, say, the Euclidean norm squared which is the standard Riemannian structure, the Euclidean structure. This vector field, this is though coming from you. So sort of, this is your input, the direction in which you'd like to move. So like, I look at a matrix, I say this row is not scaled properly. Right? So this column is not scaled properly. Okay, so there is choice here coming from the vector field. But the nice thing is that, so no matter what choice we make, as long as the choice is pointing, as long as our choices are pointing in some direction, for instance, towards the target matrix scaling, we don't know what it is, but it sits there, then there is something giving us monotonicity in the dynamics. Okay, so sort of we're always improving in some sense.
So F of F sub t is the optimization problem we need to solve.
I'm going to give like 5 examples. So, and the first one is matrix scaling, where you can think about the underlying convex body as just non-negative, let's just say the square case, n by n matrices, and then I'm just putting here some global normalization, so the sum of the entries is 1. That normalization is easy to achieve just by scaling the whole matrix, right? So now you start at your input matrix scaled, so let's say this is just some normalization so that all the entries are equal to 1. what are your directions? What's your FT? Well, if you want rows and columns to be normalized, then you can imagine that your directions look like this. Either you want to move in the direction that sort of notices that, I mean, think about this constraint. This is saying something about the sum of, this is the sum of the entries in the row or the sum of the entries in the column. Okay, and it might be too large or too small. So you have a plus or minus. Those are your directions. And you can see if you move in these directions just in the Euclidean geometry, you will not get anything that looks like matrix scaling. We'll get something strange because you're just, you will be, like if in the Euclidean geometry, you would just be subtracting off a multiple of one of these vectors. But if you take your convex function to be the entropy, the negative Shannon entropy, then you get, if you look at these dynamics, basically the Hessian here is like 1 over xij. So now when you multiply over here, you get the derivative is multiplicative. So if you use this, you can look at what the dynamics give you. They're exactly multiplying a row. When you move in this direction, you're multiplying a row. If the coefficient is positive, you're multiplying it by a number bigger than 1. If it's negative, by a number smaller than 1. Okay, so matrix scaling you can think about as like the NOP Sinkhorn algorithm, Sinkhorn NOP. You can think about it as just say, choose a row, or choose, if you want, you could choose some linear combination of rows and scale them all to be so that the row sums are 1, and then you can switch to the columns. But in general, one thing I wanted to point out here is that there's no, like, alternating is not something which is central here. You could, really, you're always, this was too big. Really, the point is, anytime that there's some, think about it, so even think about not the doubly stochastic case. Think you just have targets, you just have prescribed values for the row sums and the column sums. So every time your matrix doesn't have one of those prescribed values, you can move a little bit in that direction. And what the, I had it, sorry, I actually put it for myself. And what this tells you is that as long as the set of directions is consistent in some sense, for instance, they're the set of row and column sums of some actual matrix, then you're always improving because you're always moving towards that matrix. So here, for instance, this algorithm that I described converges to whatever your target marginals are, if and only if there actually exists some valid scaling of the input matrix where this relative entropy, this is your Lyapunov functional, where it starts less than infinity. If it's less than infinity, you will drive it to 0. And when is it less than infinity? It's less than infinity if and only if basically here x and y have the same 0 non-zero pattern. So of course, if by the way, if some matrix has a scaling, then of course the scaling has the same 0 non-zero pattern because you only multiply things by positive numbers. So this says that whenever, take whatever target marginals you want, whenever there exists a good scaling, this algorithm will find it. And the reason that it converges is because whatever the good scaling is, you're always getting closer to that in the correct geometry. Okay, so that's just, there's a, yeah, this is very classical. There are many things we didn't talk about here. For instance, like whether, this algorithm is not strongly polynomial, and so there are many, but like the basic idea is very powerful, and in fact, almost all of the general ideas that one has to tackle occur already here, even though you don't have many things there are many things you might not want about this. Basically, this algorithm could take too long in terms of how much accuracy you want. Like if you want to get this scaling down so that every row or column is within 1 plus minus epsilon of the target, this in general will just the standard analysis, or in this algorithm in general, will give you something which needs, it's continuous time, but 1 over epsilon squared steps of having to switch between rows and columns before you converge. For many reasons, that's too slow. That would correspond to exponential time. But this is just a basic example of what's happening here. So let me tell you a couple of others, which are perhaps even more surprising. So here's a Ross theorem for 3-term progressions in the integers. So it says that if you take any subset of 1 up to n, which is big enough So it has at least a constant proportion of the elements, or here is even the best quantitative bound. If it has at least n over log n elements up to some log n factors, then it will contain three-term progressions. So that's, this is a classic theorem in number theory, has a long sequence of works. There's a conjecture of Erdős-Turan that you should be able, that basically you should be able to get this to be n over log n, but the counterexamples, there's a counterexample due to Berend are very far from this. So, okay, it's a very nice problem, very well studied. The best bound, improving on the power in this log-log factor is due to Thomas Bloom. And in 2015, his main, sort of new tool improving this is some kind of, so structure theorem about the Fourier spectrum of such subsets. And so let me just tell you how you can instantiate this setup so that his main structure theorem just falls out of the general theory I told you here, just sort of like just exactly knowing this theory and nothing else. So there, if you take your convex body, okay, so G here is say a finite abelian group. Take your convex body to be the set of probability measures on a finite abelian group. You start at the uniform measure. Here, the unknown target is the characteristic function of the set A. You know the target, but the dynamics don't know the target. And then the directions you move in, they're just the characters. So at every point in time, if there's some character which is unusually large for your set, then you move in that direction. And the notion of progress is just the entropy. Some fairly technical proof with lots of counting arguments and binomial coefficients and so on. Okay, if you just set up the dynamics in this way, you prove this lemma of Bloom. So by the way, what's the point here? It's just to give some indication of this seems like it's this continuous optimization setup. Here is some very discrete problem where this this has a lot of this technique is very useful, just in giving some convergence. And by the way I think about an algorithm like this is that sort of you start at the uniform distribution and then and so by the way, I'm not stating the Fourier analytic lemma, but it relies on the fact that if I start in the uniform distribution on my group and I keep moving in the direction of my set A along directions corresponding to, say, large Fourier characters of A, then in a very small number of steps I have to converge, which means that somehow the large spectrum of the set A is fairly simple, because there is some algorithm, which is this continuous trajectory, that discovers all of the large spectrum of A in a small number of steps. Okay, so all right, does anybody have a question? I see that nobody likes this, what I just put here. I see that. Avi?
No, everybody likes it, but I would like to know what the bottom line message. So the bottom line message is that there is some Fourier theoretic lemma behind all this. That Fourier result behind all this focus about sets that don't have a three-term progression. And what you're saying is that this can be derived from the speed of convergence of this very simple lemma.
Yeah, and in fact, the classic Cheng's lemma in this setting, which is what you would get if you just look at the 1 over epsilon squared analysis for gradient descent, is not, at least as far as anyone knows, useful for this problem. You have to beat the 1 over epsilon squared. You have to change the 1 over epsilon in some way to get this progress. But even this is nice. Sort of this Fourier analytic progress relates to the major problem in first order methods, which is sort of this 1 over epsilon squared dependence that gradient descent has. So, okay, so this is just, I know, yeah, okay, so this is, but there is a paper, you can look at it, so you should be surprised if nothing else. No, by the way, continuous time here has no the reason I'm working in continuous time is just because everything is much simpler there. So like all of this stuff is like for instance, the fact that you're always converging in discrete time, this is some, whatever the Pythagorean theorem for so on. But in continuous time, everything is very simple, and I feel it's nice to separate the discretization. There's some continuous trajectory that's beautiful, and then okay, in the real world we have to discretize it. So this is but everything here is discrete in the sense that I'm just changing my control function some finite number of times. So.
No, my question is, can you prove the same thing you proved by continuous thing using discrete scaling?
Yeah, what does it mean, discrete scaling?
So your condition, you want to get sums of certain sets constants.
Yeah, the answer is yes. The point is that along this trajectory, the vector field will be a piecewise constant. So this is a discrete algorithm. The point of for some things, the continuous thing is nice, but it's, I really just stated like this because it makes you can exactly describe the dynamics. You don't run into all of these issues about, okay, there's an epsilon cubed term and I need to run around with it all the time and so on.
In this case, things are okay, but you know that discrete continuous case is too nice. Like Newton continuous, Newton method, it's very fine, it's converges always. But the differential equation explodes on finite interval.
Here you do get explosion in some sense. It corresponds to the 1 over epsilon squared versus 1 over epsilon issue that's sitting behind here. There's a, I'm not suggesting, like the continuous something, it's not even an algorithm. It's just, I'm just giving you a trajectory. It's just, if you have such a trajectory there, for instance, there are obvious discretizations, there are clever discretizations, you can do all kinds of things. I'm just suggesting this sort of this general setup where, there's nothing special about continuous time. There is, it's nicer, but that's the only reason I say it like this. Like nothing powerful is happening in the continuous time setup here, except that it's just easier, I can write down the differential equation, that's nice. Yeah.
So in both of the examples you gave, you chose a phi which was like the Shannon entropy.
Mm-hmm.
So is this a nice universal thing, or is there something about the problem that points you to a good phi?
Okay, so good question. The answer is, the most basic answer to this is that when the underlying convex body is a simplex plus some additional constraints, then under the relative entropy, the diameter of this, if the dimension is n, the diameter of the convex body is kind of like log n, right? The sort of the maximal entropy of a distribution on n things is log n. Whereas if you normalize things correctly, in the Euclidean case, the diameter would be something like square root of n. And the diameter affects how long it takes you to converge. So this log n versus square root of n can be a huge deal. It can be exponential time versus polynomial time. But okay, let me give a couple more examples. Okay, so here's the result we proved with David Storer and Prasad Raghavendra a few years ago. There are all kinds of polytopes associated to NP-hard problems, like the traveling salesman polytope, or here's the cut polytope. It's the convex Hall of n by n matrices that are tensors of some Boolean vector. If you can optimize over this polytope, you could, efficiently, then you would prove that P is equal to NP. And so people, in complexity theory, you would like to prove that, okay, well, we can't prove that P is not equal to NP, but at least prove that that the methods we know cannot optimize over this polytope. So here is a theorem that we prove that if you try to write this polytope, the cut polytope, as the projection of some of the feasible region of a semi-definite program, okay, then the dimension of the semi-definite program that you use has to be really big, exponential in n to some power. And therefore, if you want to try and prove that P is equal to NP via sort of standard mathematical optimization methods, well, it's not going to work. There's a long history here, but this is the version for semi-definite programs. And so let me just tell you again how it's related to your question, how this is instantiated. In that case, the convex body K, you can ignore what's written here, but basically it corresponds to some classical quantum states. So some quantum state on r qubits and n on r quantum bits and n classical bits. you start in the maximally mixed state. Your regularizer is this is the classical quantum entry, but this is the von Neumann entropy of the system. And the directions, for whatever reason, it's a good reason, but I don't want to discuss it now, are the squares of low-degree polynomials. So now if you follow this basic method, you look at this trajectory, basically you can associate to a low-dimensional spectrohedron some quantum state, and then you can try to see, you can try to basically use this trajectory to approximate that, starting in a very simple quantum state, so the sort of the quantum state that's maximally mixed, you run this trajectory approaching your state along these low-degree squares of polynomials, and what this basically shows is that any low-dimensional spectrohedron can be approximated by a sum of squares, a low-degree sum of squares spectrohedron, and then for that we have explicit lower bounds that such things cannot be lifts of the cut polytope. Okay, so the only point basically here is that, okay, so there's some interesting theorem that one can prove with this setup. Now we're talking about a different convex body, a positive semi-definite cone, and again some notion of entropy. So, okay, so, but there are situations where the entropy is not the right thing to use. So here's here's the theorem of Batson-Spielman and Srivastava, which it says that every graph G can be spectrally approximated. Basically, it's the quadratic form associated to the graph can be approximated by the quadratic form associated to some sparse graph on a that's supported on a subset of the edges of G of linear size. So if you this is a famous theorem about graph sparsification that was open for a very long time. But every graph, even dense graphs, there exists a graph that's supported on a linear size subset of edges that spectrally approximates the graph. That's their theorem. It was shown by Alan Zhu, Liao, and Orecchia that actually the iterative algorithm they give for constructing this sparsifier can be, again, viewed in this framework where now the convex body is, again, the spectrohedron normalized to have trace 1. By the way, the way you encode a graph in this body is just you think about the graph as the associated quadratic form. And but there, the regularizer, it turns out, that you use in order to get a linear number of edges is minus trace square root of x. Okay, so this has some. If you just use the entropy, you would get n log n edges. You would actually recover. It's also discussed in this paper. A result of Spielman and Srivastava. But if you use this beautiful regularizer, which has seen a number of applications since then, then basically the fact that this sequence of approximations converges fast gives you, like, the number of steps is the number of edges in the approximator. So the fact that you can only do a linear number of edges means you get a graph on only of linear size. And the directions here are the ones you would expect. That you just you move in the direction of edges of the graph. So here xe, what does it mean? I mean, some vector associated to the edge of the underlying graph. Okay, so again, you can, once you set this up, now the analysis basically, some analysis which actually, it looks beautiful and mysterious in Batson-Spielman and Srivastava, becomes much more clear what's going on here. It's really just an instance of this kind of thing I talked about. It's a bit more complicated because there is an upper bound and a lower bound, but okay, but you can read about it. Okay, let me mention the one last application. I'm mentioning it for a reason, which you don't have to. I'm not gonna, like, Avi was worried that I would talk for ad nauseum about this, but I'm not going to say almost anything, which is just that you can use these methods also for problems in online algorithms. I will tell you why I'm mentioning this in a second. Really, I'm just putting up this slide here so that you can, okay, first of all, again, you can, they solve some 30-year-old open problems, so, okay, so you should, so something useful is going on. It's not just like regurgitation of something already done. And I'm just showing you can look at these regularizers, things that look like entropies, things that don't look like entropies. There's all kinds of beautiful things going on here. Okay, there's some, okay, but let me focus on one aspect here. So in this field of online algorithms, what happens, you have a sequence of inputs that arrive over time. At every point in time, your algorithm has to take some action based on only what it's seen so far. And then your actions have some cost associated to them, and you want to say that the total cost you pay is not too much worse than the cost paid by some omnipotent algorithm that can see the entire request sequence in advance. So this is called, so you compare, you want an algorithm that, has to deal with uncertainty about the future, but does almost as well as an algorithm that can see everything in advance. This is the whole field. And so what happens if you frame these problems in this setup is actually that, your algorithm is a point here which is moving, but the point that you're approaching in this Lyapunov functional is not stationary anymore. It's not just some fixed point like something you're trying to approximate, or you can think about this as the optimal offline algorithm, so it's moving around. So you get some setup that looks kind of like this, and in general, where is this vector field coming from? Well, at every point in time, you get some input, and you need to take some action that addresses this input. And so that input tells you something about the optimum, which is unknown. You don't know what the optimum is because, it can see the whole future, but you know that the optimum must also respond to this input. So this gives you a tiny bit of information about it, and now you can use this information somehow. And so the point is that this monotonicity holds for any y inside the convex body. So it also holds for this optimum that you don't know. Even if it's moving around, the optimum might change, but at every point, if the information you're getting tells you something about the optimum point, you move towards it, even if the optimal is changing. And if you do things in this setup, you notice that now, though, in order to say, for instance, that first of all, if the optimum runs away from you, you would like to say that I don't care about that. That means the optimum is somehow spending a lot of cost. So great. If the optimum is spending a lot of cost, I'm willing to keep chasing it and spending cost. But you'd like to say if the optimum is not moving, if it's staying in the same state, then I'm getting closer to it. And you can see that once you put things in this setup, you need an additional property from this potential function, which is that I don't want it to be the case that this point y, the red point here, could move a little bit and then suddenly make my distance in this potential huge. Right? Then the picture, it wouldn't look like I'm chasing the point. The point would move a little bit, and now everything I learned about it is lost. So this means that you need some smoothness property in the first coordinate in order to apply it in these fields. And I just want to say that this is very much related to sort of the bit complexity problem, because you can think about what does it mean that I have smoothness. It means that if I take if I have y or some perturbation y prime, I want to say that the algorithm basically does the same thing or converges in the same way, which is exactly saying I don't want to be too sensitive to the initial conditions. So the reason that this problem took a long time to solve is exactly because of this problem of smoothness in some sense. So here in the regularizer, it looks like some trivial way that we fix it. We add in some shift to the entropy. So you can think about this as first you take some distribution and you add some noise to it, and now you only look at yourself with respect to this noise distribution. If this was so, unfortunately, when you add it there, lots of other things go wrong. Analysis is somewhat complicated. But this is another theme that comes up fairly often, which maybe is useful, for instance, in operator scaling, which is the idea that if you want your algorithm to have nice, say, bit complexity and be stable, then just prove convergence with respect to a potential function that's not allowed to look too closely at the matrix. So there's a bunch of examples of this setup. Now let me go back to relating it to Brascamp-Lieb and operator scaling. Yes?
Get back to that, please. So this type of results, about 20 years ago, there was this popular things called boosting.
Mm-hmm.
And things like portfolio, they use portfolio
Yes.
recommendations. It seems like
Yeah.
similar stuff.
Yeah, this is all like the bread and butter of this online learning, and it was boosting and exponential weights and so on. One, for instance, thing, okay, so you can even ask what's the point of having like this general theory? Maybe it's a theorem that gives you all these results that were obvious to see beforehand. So here's one example where the dynamics are extremely complicated. We cannot write down a closed form anymore for the dynamics. But still, you get some convergence of this system. So.
But in that activity, I remember what was happening historically. There were all those multiplicated exponential weights.
So for instance, I mean, Avram Blum worked on this problem even now 20 years ago, trying to use exponential weights to solve it. So you need to do something.
There was interesting development. So, and this is what led me to scaling. So I recognized that the Bregman distance is there. And I told Manfred Wormuth, who's like, and now, apparently the Bregman distance is like the main expression in that stuff.
Yeah, that's true.
All those algorithms which you get.
They're essentially all analyzed in this setup. Yeah, I think this is, I mean, this is just my, my love letter to Bregman divergences. It's very, very beautiful that you can have such a simple general theory that applies in all of these situations that seem very disparate.
By the way, have you contacted him personally? He's still alive.
Bregman, if you're watching, no.
You asked a lot of questions from my head, yeah. But the question about personal communication,
Yeah, let's save those for after the talk. Okay, so let me just let me prove one thing, which is even in a different setup that goes along these methods, but that's related to the Brascamp-Lieb problem. So okay, so there is what's called the geometric setup for the Brascamp-Lieb problem, and I believe this was mentioned already, but this is a situation in which it's clear, like in which Brascamp-Lieb feasibility is true for all datum that satisfy the geometric property, and then I would say that the main application of operator scaling in studying this the Brascamp-Lieb problem is taking any set of datum for the Brascamp-Lieb problem and figuring out a way to convert it into the geometric setup where you know the answer. And then, of course, this is where the operator scaling comes in. But now I just want to talk about the geometric setup because it's by the way, everything I'm saying, it's supposed to motivate talks coming afterwards. So in the sheet, we'll talk about perhaps the right way to think about these things, and Lapchi will talk about some related problems. But here's the geometric setup. You have a bunch of Euclidean subspaces of Rn, and let Pi be the orthogonal projection onto Ei. And you're going to assume that there is this, what's called this frame condition holds, that you have some constant such that if you sum this Ci times the projection Pi, then you just get the identity map on Rn. Okay, this is the assumption. This is the geometric setup in Brascamp-Lieb. And now let me give you a conclusion which was shown by Carlin and Cordero Araskin to be equivalent. Okay, here I'm doing it in the Gaussian setting. Things are perhaps a little bit simpler, but let's just say morally equivalent to the Brascamp-Lieb inequality. I mean, in general, the Brascamp-Lieb inequalities are known to be all about statements that it can be interpreted as subadditivity of entropy. But in the geometric setup, it's very easy to write what's going on there. So, okay, so you have such a frame. Now, let Z be a Gaussian on Rn and Zi be a standard Gaussian on the subset Ei. Then what you have here is that the relative entropy, so now for any random vector x, so for any distribution, the relative entropy of that distribution with respect to the Gaussian measure, this is the Carroll divergence, is at least sort of this weighted sum of entropies. And this is very natural subadditivity of entropy. It says that, right, it says that the information in X with respect to the Gaussian measure is always more than if I decompose the set of information into pieces and measure each piece separately, right? Because I miss out on all the cross terms that might be giving me more information. So this is an entropic formulation of the geometric Brascamp-Lieb. So let me just give you a proof of this using these kind of entropy. These entropic methods. Okay, so here's the proof. It's going to be again, if you didn't pay attention to anything, this is really beautiful. So this is a proof due to Joseph-Lehec, but it's really nice. So consider some probability measure mu on Rn, and gamma, yes, say it again? There's an, oh, sorry, D is the KL divergence. I mean, it's just, okay, this only, this is only finite if this random vector is absolutely continuous, but then this is just, if the density of x with respect to the Gaussian measure is f, this is integral f log f. So, yeah, so it's the KL divergence. Okay, so here's the setup. So you have some probability distribution mu on Rn, and gamma is just the standard Gaussian measure. And now I'm going to take a Brownian motion here, which starts at the origin. And if you don't know about Brownian motion, then just what you need to know is that at time 1, the law of Brownian motion is the standard Gaussian measure. And so if I just run Brownian motion, I will sample from the Gaussian measure at time 1. But I don't want to sample from the Gaussian measure. I want to sample from this measure mu. So what I will do is I will allow you to bias this is a stochastic differential equation. Just read it informally. I will allow you to bias the Brownian motion so that at time 1, instead of ending up in the Gaussian measure, you end up in the measure mu. So you can think there are many ways to do this. Okay, it's continuous time, so it's like maybe you don't see that there are many ways. But for instance, you could wait until time almost 1 and then just sample from mu and then just go there. Like that's not a very good way to bias the Brownian motion. But I'm saying consider all of the drifts where if I do Brownian motion plus I add a little bit of this drift, then I design the drift in such a way, this drift is adapted, so it depends on the past. I will see everything happen so far, and I will be able to push Brownian motion in the direction I want. And my goal is just to end up at with law mu at time 1. So I'm saying there's a family of such drifts that if I put them on Brownian motion, I will end up in the distribution mu. Here is the theorem of Borel and Fulmer, which is that the relative entropy between mu and the Gaussian measure is exactly the minimum energy required to push Brownian motion to sample from mu instead of from the Gaussian measure. So, okay, I mean, this statement is not obvious, but it's kind of very, it's a nice statement. So just sort of like, of all the ways of sampling from x, the one which minimizes the amount of energy I have to do to push Brownian motion there, that gives me an expression for how far apart mu and the Gaussian measure are in this relative entropy distance. At least things are going in the correct direction. You see, like if mu was just the Gaussian measure itself, then the relative entropy would be 0, and of course I don't need to push Brownian motion at all. It will sample from the Gaussian measure all by itself. Okay, so now here's a video. I don't know that people want to see this video. What is the video? It's I just had this video and it's relevant, so why not? What's the video? There's some random walk on this is just an n by n torus here, and you cannot see this point will split in a second. The red point is doing a random walk. The blue point is doing the entropy optimal walk that ends at time 0, which is coming soon, which ends uniformly distributed on this green set. Okay, and so you can just see what's happening here. Like this blue point, as time is approaching 0, like this is representing how much drift it's feeling. It's feeling a lot of pain now. It's getting very desperate because it needs to end in the green set at time 1, and okay, this was a torus, and so it was confusing because the whole time it was pushing to go this way, but it's because this is the same thing as this. Anyway, that was a picture of on the one hand the red point was doing random walk, and the other point the blue point was doing the minimum energy bias of the random walk to end, instead of in the uniform measure on the torus, which is where the random walk ends up, to end uniform on this green set. Okay. It was just it was a video. People love videos. Okay, so here's let's use this to prove the geometric Brascamp-Lieb. This proof is due to Joseph-Lehec, based on a related argument of Mori earlier that's unpublished. Okay, so remember, our goal is to prove this subadditivity statement for the relative entropy. So, so we have this random vector x. Let Vt be this energy optimal drift, the one, the way to push Brownian motion using as little effort as possible, so that at time 1 we end up according to x instead of according to the Gaussian measure. Okay, so by what I just said, the relative entropy from x to the Gaussian measure is exactly the amount of energy, the expected effort, energy expended by this drift. By the frame condition, I can write this exactly as I can write Vt squared exactly as the sum of Ci times Pi Vt squared. And, okay, and that was the, why is there, okay, everything made sense here except the integral doesn't make any sense. What happened there? Okay, sorry. I don't understand why this should not be here. Oh, come on, PowerPoint. For PowerPoint, this integral it's going to tell me this integral is one object that cannot be edited separately. Oh, hold on, I will make this make sense in a second, hopefully. All right. Okay, good. Sorry. So this is by the frame condition. And now this step is, again, just by optimality. Pi Vt is some drift which on the subspace Ei ends in the distribution Pix. And therefore, by optimality, by this characterization, the energy expended by this drift is at least the relative entropy between Pix and Zi. So that's it. That's the proof. And it's a really beautiful proof because what it just says is, sort of do the entropy optimal way of sort of pushing the Gaussian measure to x, and just note that on every subspace, this also gives you a way of pushing Pix, of pushing the Brownian motion on that subspace to Pix. And okay, so the total energy I use has to be, to do this is only is only more than the energy I need to achieve each of these things separately. And the frame condition is just what tells me that the amount of effort I use can be split between the different pieces. So this is okay. I really like this this proof. Let me end now on. Okay, that was the geometric BL thing. This is my last slide. It's going to end with an open question. So that was the geometric Brascamp-Lieb, but there is this major step in proving the general case from the geometric case, which is the operator scaling problem. And what you should probably ask yourself, and maybe Leonid has the answer anyway, which is that sort of, what about these things based on capacity? Does that fit naturally into this framework? And the answer in this current framework, I believe the answer is no. And in the next talk of Nishith, he will tell you the answer is yes. But let me mention, again, this was another a blog post, that in the rank 1 scaling case. Okay, so here's the theorem of Barth and Forster, which corresponds to operator scaling in the rank 1 case. I have a bunch of unit vectors, x1 up to xn. There exists some linear mapping so that if I look at the rescaled vectors under this linear mapping, they're in isotropic position after I apply this mapping. This is the rank 1 case of operator scaling, assuming that these things are in general position. Okay, so I claim that you can get this operator scaling A via entropy maximization in the rank 1 case. And then my question, which I would love to know the answer to, is can you think about the general case as entropy maximization? Here, yes?
Okay, so first of all, the capacity in the classical case of scaling
is the dual.
No, it was well known that it's related to the Bregman distance. Okay, this case, so here you essentially, with this case, here essentially you scale polynomial. Here is irrelevant. The fact that, so here you start, in this case, you start with the determinantal polynomial. Determinant of linear combination of those rank 1.
Yeah.
Essentially, you scale just that polynomial.
Yes.
To candidate doubly stochastic, yes.
Mm-hmm. Yeah.
For that case, it's well known that it's the same as this Kurzweil-Kloebner stuff.
Yeah. I mean, this program is exactly the dual to the capacity in this case. And in the matrix scaling case, the entropy is the capacity. The log capacity is like the log partition function, and so it's.
You can push this thing. You can push this thing a little bit. So here it's a very special rank 1 case for operator K. So it's kind of on one side quantum, another classical.
Yeah. The question is, can I think about the general case as entropy maximization?
In one case, you can reduce to scaling of some polynomial. So potentially there will be something there.
Okay. I'm interested in the higher rank case.
Just a second. Maybe you finish the slide. I think
Oh,
many people don't even know
yeah.
what he's going to say.
So good point, Avi. What am I going to say? Yeah, so if you take these vectors, then you can define what's called this determinantal measure, where it's a measure on subsets of size k. That's just where the probability of sampling a subset of size k is the determinant of the matrix formed by the vectors in the set S. So from the Cauchy-Bonnet formula, one can check that this is indeed a probability measure on subsets of size of n elements of size k. And then if you minimize, so now if you minimize the relative entropy over all distributions take all probability measures on subsets of size k, minimize the relative entropy to this measure, subject to these very seemingly weak constraints. So these like if you're going to have some scaling that satisfies this is some set of constraints you're going to need, but these are just the one-dimensional marginals. If you think this is the probability that for any element I, the probability that it's in the set S sample from this distribution is k over n, which is just, it's just corresponding to the fact that, like every element appears equally often in a set sampled from S. If you solve this optimization problem, the optimizer gives you this map A. So it's written, I don't know actually any place it's written except on this exactly is written except on my blog, but it is written there. And so in the rank 1 case, you can think about operator scaling as entropy maximization or relative entropy minimization. My question, which you might have to wait till after the Sheath's talk to think about, is whether something is true more generally in the higher rank case. Because every time I see capacity, it looks like it should be the dual of entropy. At least in the rank 1 case, it is the case, but I don't know how to say something more generally. And in particular, because the capacity is not, like log capacity is not convex with respect to the Euclidean structure. So already, everything I'm saying here doesn't apply in the higher rank case. So that's my open question that you can think about now or during the Sheath's talk. Well, let me end there. Thank you.